Our sun, it looks like a simple, bright ball in the sky, but it's really a churning, chaotic sphere of plasma, and it's all driven by these incredibly powerful, invisible forces. For decades, we've been trying to map these forces, to get a handle on them so we can predict their violent outbursts. Well, today, we are looking at a huge breakthrough that gives us a completely new way to see our star in 3 dimensions. And honestly, it could change everything we think we know about space weather.
You see, everything from those beautiful auroras to solar storms that could, potentially knock out our power grids, it all starts with the sun's magnetic field. So to predict this space weather, scientists absolutely have to map the magnetic landscape of the sun's most active regions. But here's the thing, it's not the whole sun we need to see. It's these small, tangled, super complex areas where all that energy gets stored, up, and then, boom, released.
And that right there is the multi-billion-dollar question, isn't it? I mean, think about it. We can't just send a probe out there with a compass. We have to decode the light that travels all that way to reach us. And that light is carrying secrets that have been incredibly, incredibly difficult to unlock. It's a puzzle that has truly stumped scientists for generations.
Okay, so why is it so hard? Well, it all boils down to a kind of double trouble. There are 2 fundamental problems that are all tangled up together, and until now, we've pretty much had to try and solve them one at a time, which doesn't really work.
So this challenge, it really comes in 2 parts. First up, we have the direction puzzle. Our instruments are great. They can tell us that a magnetic field line is running, say, east-west, but they can't tell us if it's pointing east or pointing west. At the very same time, we've got the depth puzzle. We can see the sun's surface, but it's not flat at all, and we have no idea what the true physical height is of the thing we're looking at.
Let's dig into that first puzzle a little more. It's officially called the 180-degree ambiguity. Basically, the data we get from the sun gives us a double-ended arrow. It tells us the orientation of the magnetic field, but not its specific direction. Trying to map a magnetic field with that kind of data? It's like trying to navigate with a compass that's broken, a compass that points to both the north and south poles at the exact same time. It's fundamentally ambiguous.
And then, of course, there's the second puzzle. The sun's surface is not some smooth, perfect sphere. Nope. In areas with really powerful magnetic fields, like in sunspots, the surface is physically pushed down, creating these deep valleys. It's an effect called the Wilson depression. So when we look at the sun, we're not seeing a flat map at all. We're seeing this rumpled, distorted landscape, and we don't really know how deep any of those valleys go.
So, with this massive 2-part problem of direction and depth, how have scientists even tried to solve it in the past? Well, the traditional approach has been to just tackle one piece at a time, which, as you can probably imagine, only gives you an incomplete picture.
So the way it used to work is that these traditional methods would first try to solve that 180-degree direction puzzle. And to do that, they usually had to just assume the surface was flat. Then, in a totally separate, super complex step, they would try to go back and correct for the height. This whole multi-step process was slow, it was computationally a nightmare, and it often led to all sorts of inconsistencies. You just couldn't get a single self-consistent 3D picture out of it.
But now there's a new detective on the case. It's a new method developed by researchers at the University of Hawaii and the National Solar Observatory, and it has this great nickname, HDD, or the Haleakala Disambiguation Decoder.
So what's the actual breakthrough here? What's the secret sauce? Well, unlike all those older methods that had to wrestle with the direction and depth puzzles one by one, this new AI, it solves both problems at the exact same time. It takes those 2 hopelessly tangled inputs and produces one single coherent output. It's a total game changer. And the process itself is surprisingly straightforward, really. You just feed the AI all the messy, ambiguous, distorted data right from the telescope. The AI model then gets to work, processing this whole 3D data cube, and what comes out on the other side is a clean, physically consistent 3-dimensional map of the magnetic field.
But, and this is a big but, this isn't just any old AI. It has a secret weapon that makes it fundamentally different from other machine learning models that are out there.
Most of the AI we hear about is trained to recognize patterns, right? It looks at millions of pictures of cats so it can learn what a cat looks like. But what happens if the real sun doesn't look exactly like the computer simulations the AI was trained on? That's a huge, huge problem.
And this quote from the research paper really gets to the heart of that limitation. Now, Muram is a type of highly realistic solar simulation. So an AI that's only trained on those simulations can only ever find answers that look like them. If the real sun is doing something new or unexpected, a purely pattern-based AI would be completely lost. It's basically trapped by its own training data. This is where that secret weapon comes in. It's a field called physics-informed machine learning. And instead of just showing the AI a bunch of examples, the scientists also teach it the fundamental laws of physics. So the AI isn't just guessing based on patterns anymore. Its answers are constrained by the actual rules of the universe, which forces its answers to be physically realistic.
So what law did they teach it? It's a core principle of magnetism. And in simple terms, it says that magnetic field lines don't just have beginnings or endings. They always have to form complete, unbroken loops. The technical name for this is the divergence-free condition. By forcing the AI's 3D map to obey this one simple law, the model can finally untangle the direction and depth problems to find the one single solution that is physically possible.
And the result of this whole new approach? Well, it's like the difference between looking at a fuzzy, out-of-focus photograph and a crystal-clear 3D model. For the first time, we can finally see the full picture.
And the difference is absolutely stunning. Just look at this. On the left, you've got the before, that messy, ambiguous data we started with. It's a jumble, it's hard to make any sense of. But on the right, you see the after. That's the output from the HDD model. It is a clean, consistent, and physically accurate 3D reconstruction of a sunspot's magnetic field. You can actually see the structure, the loops, the entire magnetic architecture. It's incredible.
So why does all this matter so much? Well, with this clear 3D map, scientists can now accurately calculate things like electric currents and magnetic forces, the very engines that drive solar flares and eruptions. This isn't just about getting a prettier picture, it's a fundamental leap forward in our ability to understand and maybe one day forecast the space weather that directly impacts us here on Earth. When you step back, this is more than just a story about the sun. It's really about a new kind of partnership between human knowledge and artificial intelligence. By encoding the fundamental laws of nature directly into our machines, we're not just creating better pattern finders, we're creating entirely new scientific tools. And it really makes you wonder, what other cosmic puzzles could we finally solve, not just with more data, but with smarter machines?